See also, searching for the Big Bang quasars and pulsars Reber Ryle. In context. Key astronomers Walter Baade, Fritz Zwicky. Before 1914, American astronomer Walter Adams first describes white dwarf stars, which are now known to be involved in common novae. 1931, Subramanian Chandrasekhar calculates the greatest mass a white dwarf can have. After 1967, Anthony Hewish and Jocelyn Bell Burnell discover pulsars, which are found to be fast-spinning neutron stars. 1999, a survey of the light from Type 1a supernovae shows that the universe's expansion is accelerating due to an unknown quantity known as dark energy. In 185 CE, Chinese astronomers recorded a phenomenon they called a guess star. The star had appeared in the direction of Alpha Centauri, the closest star system to Earth, and had shone brightly for 8 months before vanishing. This is probably the first recording of a supernova. Mysterious new stars have appeared several times across the centuries. In 1572, Danish astronomer Tycho Brahe named one a nova, meaning new. With the development of telescopes, novae became subject to closer scrutiny and were found to be faint stars that lit up with a great intensity for short periods. It was not until the 1930s that two astronomers at Caltech in California, Walter Baade and Fritz Zwicky, calculated that some novae released much more energy than others. For example, they calculated that S Andromedae, a nova seen in 1885, had released the equivalent of 10 million years of the Sun's output all at once. Baade and Zwicky dubbed these incredibly energetic events supernovae. Core collapse. In 1934, Baade and Zwicky suggested that a supernova was the core of a large star, collapsing under its own gravity after running out of fuel. The collapse was so powerful that it annihilated matter, releasing a huge amount of energy in accordance with Einstein's equation E equals mc. What was left was a neutron star, a body composed of only neutrons that were packed together like the particles in an atomic nucleus, only on a much larger scale. A neutron star is only about 7 miles across, but has huge density and gravitational pull. Neutrons can be packed more closely than atomic nuclei, meaning that a teaspoon of neutron star weighs 10 million tons. The star's escape velocity is nearly half the speed of light. First detection. The concept of a neutron star remained purely hypothetical until 1967, when pulsars were discovered. Pulsars were shown to be rapidly spinning neutron stars. In 1979, a powerful burst of gamma rays was detected. This has since been attributed to a magnetar, a kind of neutron star with a magnetic field billions of times greater than Earth's. Many mysteries remain regarding collapsing stars. Only stars above the Chandrasekhar limit of 1 for solar masses will become supernovae and form neutron stars. A star above 3 solar masses goes further and becomes a black hole. There may be a halfway stage in which neutron matter degenerates even more into quark particles, the particles from which neutrons and protons are made. Quark stars remain hypothetical, but the search for them is on. A supernova in the Large Magellanic Cloud blew out this cloud of shrapnel, captured by the Chandra X-ray Space Observatory. The explosion was caused by the collapse of a massive star. Fritz Zwicky. Born in Bulgaria to a Swiss father and Czech mother, Fritz Zwicky emigrated to the United States in 1925 to work at Caltech with Robert Millikan, a leading particle physicist. In 1931, he began a collaboration at the Mount Wilson Observatory near Los Angeles with Walter Baade, a German astronomer, who had just arrived from Europe. It was this partnership that led to the discovery of supernovae and neutron stars, but Zwicky's work around this time was also instrumental in another great discovery. Zwicky calculated that the mass of galaxies, as indicated by their gravitational effects, was much greater than the matter that could be measured through observations. He named the missing material Dunkel Materie, now better known as dark matter. In addition to his theoretical work, Zwicky worked on the development of jet engines and took out more than 50 patents on his inventions. Key works: 1934 on supernovae, 1957 morphological astronomy. See also, the Tychonic model, quasars and pulsars, dark matter, dark energy. In context. Key astronomer Hans Bethe. Before 1919, Francis Aston discovers that 4 hydrogen nuclei have more mass than a helium nucleus. 1929, Welsh astronomer Robert Atkinson and Dutch physicist Frits Houtermans calculate how the fusion of light nuclei within stars could release energy in accordance with mass-energy equivalence. After 1946, Ralph Alpher and George Gamow describe how nuclei of helium and some other nuclei could have been synthesized during the Big Bang. 1951, Ernst Opek describes the triple alpha process, which converts the nuclei of helium-4 into carbon-12 in the cores of red giant stars. Until a brilliant young German-born physicist named Hans Bethe figured it out in 1938, no one knew for sure why the Sun and other stars emitted so much light, heat, and other radiation, or where their energy came from. A step toward the correct answer had been made in 1905 with Albert Einstein's special theory of relativity, which proposed that mass and energy have an equivalence. The significance of this discovery was that a small loss of mass could be accompanied by a very large release of energy. In 1919, British chemist Francis Aston found that an atom of helium had a mass slightly less than that of 4 atoms of hydrogen. Soon afterward, British astrophysicist Arthur Eddington and French physicist Jean-Baptiste Perrin independently proposed that stars might obtain their energy by combining 4 hydrogen nuclei to form a helium nucleus with some loss of mass, which was then converted to energy. Eddington thought this might allow the Sun to shine for tens of billions of years. In 1929, Robert Atkinson and Frits Houtermans calculated how the fusion of light nuclei, rather than atoms, could create energy in stars, but the reactions were unknown. The proton-proton chain. In 1938, Bethe attended a physics conference in Washington, D.C., to discuss how energy is generated in stars. During the conference, he realized that, given the abundance of hydrogen in stars, the most likely first step in energy generation was one in which 2 hydrogen nuclei, which are single protons, join to form the nucleus of a deuterium atom. Bethe knew that this reaction generated energy. He then figured out how 2 further reaction steps could produce a nucleus of helium-4. He saw the entire sequence of reactions, called the proton-proton chain, as the main source of energy production in stars up to about the size of the Sun. The proton-proton chain joins protons to eventually form helium-4 atoms, releasing energy as gamma rays. The CNO cycle. Whereas the core temperature of a star rises slowly as star size increases, the amount of energy it produces rises much more rapidly. The proton-proton chain could not explain this, so Bethe investigated reactions involving heavier atomic nuclei. After hydrogen and helium, the next heaviest element present in appreciable amounts in higher mass stars is carbon, so Bethe looked at possible reactions of carbon nuclei with protons. He found a cycle of reactions, called the CNO cycle, during which hydrogen nuclei fuse to form helium in the presence of heavier elements, which seemed to work. Bethe's findings were quickly accepted by other physicists. Hans Bethe. Hans Bethe was born in 1906 in Strasbourg, then part of the German Empire. From a very early age, he displayed a high ability in mathematics. By 1928, he had completed a doctorate in physics. With the rise of the Nazi regime, Bethe emigrated first to Britain and then to the US. His work during World War II included 3 years at the Los Alamos Scientific Laboratory, which was engaged in assembling the first atomic bomb. After the war, Bethe played an important role in the development of the hydrogen bomb. He later campaigned against nuclear testing and the arms race. In addition to his work in astrophysics and nuclear physics, Bethe made major contributions to other fields of physics, including quantum electrodynamics. He continued to work in all these fields until his death in 2005, at age 98. Key works: 1936, 37 Nuclear physics. 1939 Energy production in stars. See also, the theory of relativity, nuclear fusion within stars, the primeval atom. In context. Key astronomer: Kenneth Edgeworth. Before 1781 and 1846. The discovery of Uranus and Neptune leads to discussion of where the outer edge of the solar system lies. 1930. Pluto is discovered. Astronomers Frederick C. Leonard and Armin O. Lustner suggest there may be similar bodies out there. After 1977. Charles Kowal discovers Chiron, an icy centaur beyond Saturn. 1992. A trans-Neptunian object is discovered by David Jewett and Jane Liu. 2005. The discovery of Eris, a TNO of a similar size to Pluto, and TNOs Haumea and Makemake lead to Pluto being demoted to a dwarf planet. In 1943, Irish astronomer Kenneth Edgeworth suggested that beyond Neptune and Pluto, there existed a disk of icy bodies that were formed at the dawn of the solar system, but were too small and widely spaced to accrete into a planet. From time to time, they were nudged into the inner solar system, where they appeared as comets. He published his idea in Journal of the British Astronomical Association, a periodical not widely read in the US. Kuiper Belt. In 1951, in the more prestigious Astrophysical Journal, a Dutch-American astronomer named Gerard Kuiper suggested that such a disk once existed but had long since been dispersed by the effects of Pluto's gravity. It came to be called the Kuiper Belt, though some astronomers now use Edgeworth-Kuiper Belt. Then, in 1980, Uruguayan astronomer Julio Fernandez realized that a belt of cometary nuclei beyond Neptune was needed to supply the numbers of short-period comets seen in the inner solar system. Photographs of the region were taken, a few hours apart, and these were then examined to see if any of the objects had moved, indicating that they were much closer than the stars. More than 1,000 objects have now been found in the Kuiper Belt. Most are larger than 60 miles across, since anything smaller is too faint to detect. The comets have remained what they were from the beginning, astronomical heaps of gravel without any cohesion. Kenneth Edgeworth. See also, the Oort cloud exploring beyond Neptune. In context. Key astronomer Carl Seyfert. Before 1908. Edward Fath and Vesto Slipher observed peculiarities in the spectrum of the nebula NGC 1068. 1936. Edwin Hubble classifies the shapes of galaxies. After 1951. Cygnus A, one of the strongest sources of radio waves in the sky, is identified as the first radio galaxy. 1963. Dutch astronomer Martin Schmidt coins the term quasi-stellar radio source for an object with a star-like appearance that is actually a distant, very bright source of radio waves. 1967. Armenian astrophysicist Benjamin Markarian begins publishing a list of galaxies with strong ultraviolet emissions, many of them Seyfert galaxies. Between 1940 and 1942, American astronomer Carl Seyfert studied a number of spiral galaxies that had compact, particularly bright centers, often bluish in color. His investigations revealed that there were distinctive emission lines in these galaxy spectra. He published a paper describing galaxies of this type, which later came to be known as Seyfert galaxies. They are usually spiral galaxies with nuclei that produce large amounts of radiation over a broad range of wavelengths, often most strongly in the infrared region, but also often including visible light, radio waves, ultraviolet radiation, X-rays, and gamma rays. Violent centers. Seyfert galaxies are just one variety of a class of galaxies called active galaxies. These have central regions, termed active galactic nuclei, in which an extraordinary amount of violent activity occurs. Quasars are another type of AGN. These are always a vast distance away and produce so much energy that they outshine their host galaxies, which cannot be seen. AGNs are thought to be powered by matter spiraling into massive black holes at their centers. In addition to emitting radiation, many AGNs also send powerful jets of particles into space from the vicinity of their central black holes. Some are associated with vast lobes of material that emit radio waves. Active galaxies that feature these radio lobes are called radiogalaxies. Spiral galaxy NGC 1068 is the archetypal Seyfert galaxy. It has an intensely bright active center surrounded by swirls of ionized gas. See also, spiral galaxies beyond the Milky Way, quasars and black holes. In context. Key astronomer Reginald Daly. Before 1913, British geologist Arthur Holmes produces the first modern geologic timescale, which proposes that Earth is at least 1.5 billion years old. After 1969, 72, the Apollo missions bring back moon rock to be analyzed on Earth. 1975, following analysis of moon rock, U.S. astronomer William Hartmann and others return to the giant impact theory to explain the new evidence. 2011, Norwegian-American planetary scientist Erik Asfog and Swiss astrophysicist Martin Jutzi suggest that the Moon formed with a tiny companion moon and the two later collided. Geologists had broadly put together a story for Earth's billions of years' existence by the early 20th century. But the origin of the Moon remained open to speculation. Up until the 1940s, most astronomers subscribed to a theory put forward by George Darwin, son of the naturalist Charles. In 1898, Darwin proposed that the Moon formed when a hot and fast-spinning Earth threw out molten rock that coalesced into an orbiting satellite. He suggested that the Moon had once been much closer to Earth and was slowly drifting away. This has since been confirmed by measurements showing that the Moon is moving away by about 1.5 in a year. An alternative theory, championed in the 1940s by American chemist Harold Urey, was the capture model, in which the Moon formed elsewhere in the solar system and fell under the control of Earth's gravity. However, the Moon is so big compared to Earth that most thought such an event unlikely. In 1946, Canadian geologist Reginald Daly presented a third idea. While Daly agreed with Darwin that the Moon and Earth were formed from the same material, he hypothesized that the driving force was an impact between Earth and another body, which had thrown material into orbit. Astronomers have found evidence that two small planets orbiting the star HD 172555 collided a few thousand years ago. A similar collision involving Earth probably formed the Moon. Matching rock. Daly's idea was more or less ignored until the 1970s, when the analysis of Moon rocks showed that their mineral content is a very close match to that of Earth's mantle. Both are high in silicates but have low levels of metals. If the Moon had formed elsewhere, its rocks would be very different from Earth's. If it had formed from the same molten raw materials as Earth, it would be expected to be a mini version of Earth, and have a larger metallic core. However, the rock evidence points to the Moon being made from material gouged from Earth's surface after the planet had solidified. Big splash. In the last decade, computer modeling of possible impacts has suggested an event now dubbed the Big Splash. In this scenario, a Mars-sized planet hit Earth 4.3 billion years ago, about 200 million years after Earth's formation. The impact turned both bodies into seething balls of magma. Most of Theia merged with Earth, and that splash hurled magma into orbit, mostly from the rocky outer region of the planet. This material formed the Moon. Although the Big Splash idea is very much a hypothesis at present, it remains the best guess as to the origins of the Moon. At bottom, each exact science is, and must be, speculative. Its chief tool of research, too rarely used with both courage and judgment, is the regulated imagination. Reginald Daly. Reginald Daly. Geologist Reginald Daly's contributions to the theories of continental drift, plate tectonics, and the rock cycle have proved invaluable in understanding the similarities and differences between Earth and other rocky bodies in the solar system. Daly's abilities as a geologist became clear when he was surveying the southern border of Canada, from the Pacific coast, through the Rockies to the Great Plains. The rock samples he collected during this survey led him to become a leading voice on the origins of different rock types. As early as the 1920s, Daly proposed that material ejected from Earth to form the Moon was a primary cause for the dynamic character of Earth's crust. The impact theory was a late addition to Daly's work, coming after he had retired as the head of Harvard University's geology department. Key work: 1946 Origin of the Moon and its topography. See also, the discovery of Ceres, the composition of comets, investigating craters, the space race. In context. Key astronomer: Lyman Spitzer Jr. Before 1935, Carl Jansky reveals that celestial objects produce radio waves, offering new ways to view the universe beyond visible light. 1970 NASA launches Uhuru, an orbiting X-ray observatory. 1978 The International Ultraviolet Explorer, the first telescope operated in real time, is launched. After 1990 The Hubble Space Telescope is launched. 2003 The Infrared Spitzer Space Telescope is launched. 2009 The Kepler Telescope is launched to search for extrasolar planets. 2018 Scheduled launch of the Infrared James Webb Space Telescope. In 1946, a full 11 years before Sputnik 1, the first satellite, was launched into Earth's orbit, a 32-year-old astrophysicist named Lyman Strong Spitzer Jr. conceived of a powerful telescope that would one day operate not on Earth's surface but in orbit. High above the opaque atmosphere and the light pollution, this space telescope would have a clear and unprecedented view of the universe. It would be more than 4 decades before Spitzer's dream was realized, but his patience and tenacity would eventually pay off. More than light. The discovery of extraterrestrial radio sources by Carl Jansky in 1935 revealed that there were ways of observing the universe other than by visible light. The outbreak of World War II in 1939 interrupted research into this new and exciting field. It was left to an amateur astronomer from Illinois named Grote Reber to take the first steps in radio astronomy. In 1937, Reber had made the first survey of the radio universe using homemade antennae he had built in his backyard. Soon afterward, wartime researchers found that meteors and sunspots produced radio waves of their own, this time in the microwave band used in radars. If it was possible to discover new objects using radio, then it stood to reason that other forms of electromagnetic radiation, such as infrared, ultraviolet, and X-rays, could be harnessed as tools of observation. There was a problem, however. Earth's atmosphere, transparent to visible light, is opaque to many of these kinds of radiation. The waves are absorbed by the air's molecules, reflected back into space, or scattered in all directions into a meaningless hodgepodge. As a result, it is almost impossible to garner information about most kinds of non-visible radiation from terrestrial observatories. Spitzer's 1946 paper, entitled Astronomical Advantages of an Extraterrestrial Observatory, highlighted the problem of detecting non-visible radiation. His solution was to put a telescope into space. But Spitzer also highlighted the obstacles to such a proposal: first, the technological challenge of inventing space travel, and second, that of designing an instrument capable of operating in space by remote control from the ground. Astronomy may be revolutionized more than any other field of science by observations from above the atmosphere. In a new adventure of discovery, no one can foretell what will be found. Lyman Spitzer Jr. The level of the orange curve in this graph represents how opaque the atmosphere is at the given wavelength of radiation. The major windows are around visible wavelengths and radio wavelengths from about 1 mm to 10 m. Twinkle, twinkle little star. The rest of Spitzer's paper was focused on solving a problem that had frustrated astronomers for centuries: the sky itself. Viewed from Earth, the stars appear to twinkle. This effect is caused by the star's light shifting back and forth, and rising and falling in brightness. This is not a property of starlight, but is caused by Earth's thick atmosphere. The twinkle becomes more marked as magnification increases, making the objects appear shaky and fuzzy in the eyepiece of a telescope or as diffuse smears of light in photographs. The scientific term for twinkling is scintillation. It is caused when light passes through layer upon layer of turbulent air in the atmosphere. The turbulence itself has no effect on the light, but the density and temperature differences that are making the air churn and swirl do have an effect. As the starlight passes through one pocket of air to another of a different density, it refracts slightly, with some wavelengths bending more than others. As a result, the straight beam of light that traveled to Earth across the cosmos starts to follow an ever-changing and haphazard zigzagging path through the air. A telescope or a naked eye focused on it will see a fluctuation in brightness as some of the light is directed in and out of that line of sight. The impact twinkling has on capturing sharp astronomical images is called seeing. When the atmosphere is very still and seeing is good, the image of a distant star in a telescope is a small steady disk. When seeing is poor, the image breaks up into a squirming cluster of dots. An image taken over a period of time is smeared out into a larger disk. The effect is similar to the telescope being out of focus. Improving the view. Observational conditions change constantly with the atmosphere. Before the 1990s, observers simply waited until distortions were at a minimum. For instance, high winds clear away turbulence, creating near-perfect viewing conditions. In the late 1940s, astronomers started to use movie cameras to film the sky in the hope that, among the thousands of frames filmed over time, there would be the odd, lucky image that captured the sky in crystal clarity. Another solution was to go higher. Today, the world's most effective terrestrial observatories are invariably built at the top of high, arid mountains, where cloud cover is minimal, and the air above is generally calm. With the advent of powerful computers in the 1990s, Earthbound astronomers began using adaptive optics to correct the problems of astronomical seeing. AO measures distortions in the arriving light and evens it out, just as a distorted mirror might be used to correct a deformed image to make it look like the original image prior to deformation. AO systems use minutely adjustable mirrors and other optical devices, but they also rely heavily on computers to filter out the atmospheric noise from images. Despite the dramatic improvements brought about by AO, however, a large telescope in orbit, which could observe in multiple wavelengths of the spectrum, including visible light, was the ultimate goal for astronomy. Our knowledge of stars and interstellar matter must be based primarily on the electromagnetic radiation which reaches us. Lyman Spitzer Jr. Adaptive optics requires a clear star as a reference point. As these are hard to find, a sodium laser creates a star by lighting up dust in the high atmosphere. The road to Hubble. As the leading voice in the field, Spitzer had been made head of NASA's task force for developing the Large Space Telescope program in 1965. In 1968, NASA scored its first space telescope success with the Orbiting Astronomical Observatory, which took high-quality images in ultraviolet light, doing much to raise awareness of the advantages of space-based astronomy. Spitzer's LST aimed to achieve more dramatic results than the OAO-2, observing near and far objects with the visible light spectrum. His team settled on a 10 feet 5 inches reflecting telescope and a launch was scheduled for 1979. However, the project became too expensive for its budget. The aperture was reduced to a less costly 100 in, and LST was postponed to 1983. As that year came and went, no launch occurred, but Spitzer persisted and the project continued. In the meantime, LST was renamed the Hubble Space Telescope, after Edwin Hubble, who had first grasped the true scale of the universe. By now, the telescope's mirrors had been constructed. To help reduce weight, a top layer of low-expansion glass sat on a honeycomb support. The shape of the mirrors was crucial. During construction, they were held on a support that emulated weightlessness to ensure they did not warp in space. The glass had to be polished into a curve with an accuracy of 10 nanometers. This would make it possible for HST to view everything from UV light to the upper end of the infrared spectrum. Further delays pushed the launch of HST to 1986, but then tragedy struck with the explosion of Space Shuttle Challenger on January 28, 1986, with the result that NASA's shuttle fleet was grounded for 2 years. Finally, on April 24, 1990, Space Shuttle Discovery hauled the 11-ton HST to its orbit 335 miles above Earth. Spitzer had finally realized the dream of his career, a telescope in space unencumbered by the problems of poor seeing and an atmosphere partly opaque to ultraviolet and infrared rays. A machine polishes the Hubble's mirror. Its 100 inches aperture may seem small today, yet it is the same size as the Hooker telescope, which was the world's largest telescope until 1948. Hubble trouble. The problems that had beset the mission on the ground, however, continued in space. The first images sent back by HST were so badly distorted that they were almost worthless. Was HST going to be a worse observational tool than a ground-based telescope? Analysis of the images revealed that the mirror was the wrong shape around the edge. The error was tiny, about 2/millionths of a meter, but enough to send the light captured by the outer part of the primary mirror to the wrong area of the secondary mirror, creating serious aberrations in the images. This was a worrying moment for Spitzer and his team, as it seemed as if HST might be about to prove an embarrassing failure. The Hubble Space Telescope is the realization of Spitzer's vision. It remains one of the finest scientific instruments ever made. Corrective vision. If Hubble was to fulfill its potential, it needed corrective elements added to its optical system. In effect, it was given a pair of eyeglasses. The problem with the primary mirror was precisely calculated by analyzing the telescope's images. The solution was to add carefully designed mirrors in front of Hubble's instruments so that the light entering them from the main mirror was correctly focused. 2 sets of these mirrors were fitted during a crucial service mission to HST in 1993. They worked perfectly. HST could at last be put to work, and the results were astonishing. Astronauts serviced HST 4 more times after 1993 and for the last time in 2009, in one of the final shuttle missions. The shuttles were retired in 2011, after which it would not be possible to service HST again. However, that final service added significant upgrades, which mean that HST may remain in use until 2040. U.S. astronaut Andrew Feustel uses a power tool to repair the Hubble Space Telescope during a servicing mission in 2009. Ultra deep, ultra clear. Despite its shaky start, HST has surpassed all expectations. The telescope has made 1.2 million observations to date during its 3 billion-mile journey around Earth. Despite traveling at 17,000 miles per hour, it can pinpoint a position in space to an accuracy of 0.007 arc-seconds, which is like hitting a penny coin from 200 miles away. It can resolve an object that is 0.05 arc-seconds. NASA likened this to standing in Maryland and viewing 2 fireflies in Tokyo, Japan. Astronomers worldwide began booking HST's time to see objects of interest. The archive of everything it has seen, totaling 100 terabytes and counting, can be viewed on a public website. Many of HST's observations have looked deep into space, and far back in time. In 1995, the deep field image focused on an empty patch of space, 1/24 millionth of the total sky. Combining 32 long exposures revealed a number of unknown galaxies that were 12 billion light-years away, light that began its journey just 1.5 billion years after the Big Bang. In 2004, the ultra-deep field showed objects 13 billion light-years away, and in 2010, HST used infrared radiation to make the extreme deep field of objects that existed just 480 million years into the history of the universe. To see farther than this will require the infrared James Webb Space Telescope in 2018. Nature has thoughtfully provided us with a universe in which radiant energy of almost all wavelengths travels in straight lines over enormous distances with usually rather negligible absorption. Lyman Spitzer Jr. Taken in 2004, the ultra-deep field reveals thousands of jewel-like galaxies in a variety of shapes, colors, and ages. The red galaxies are the most distant. Spitzer in space. HST is the most famous of the 4 great observatories that are Lyman Spitzer Jr.'s legacy. Between 1991 and 2000, the Compton Gamma Ray Observatory looked at gamma-ray bursts, energetic events that occur at the edge of the visible universe. The Chandra X-ray Observatory was launched in 1999, and is tasked with finding black holes, infant solar systems, and supernovae. The final member is the Spitzer Space Telescope, which entered space in 2003. One of its tasks was to peer into nebulae to pick out the hot zones where stars are forming. In 2009, the liquid helium that kept its heat-sensitive detectors cool finally ran out. Observatories can be placed in orbit around the Sun rather than Earth, where it is easier to shield them from the Sun's heat and light, and they have a wide, unobstructed view of the sky. Today, there are about 30 observatories in orbit, sending back images. NASA's Kepler, which searches for extrasolar planets, and 2 ESA missions, Herschel and Planck, are examples. All were launched in 2009. Herschel was the largest infrared telescope ever put into space, while Planck studied the cosmic microwave background. In 2015, ESA launched the LISA Pathfinder to test the technology for a space observatory that would detect not electromagnetic waves, but gravity waves. Not even Lyman Spitzer Jr. could have predicted such an advance. The Spitzer telescope was named by NASA to honor the vision and contributions of Lyman Spitzer Jr. It was initially called the Space Infrared Telescope Facility. Lyman Spitzer Jr. Lyman Spitzer Jr. was born in Toledo, Ohio, in 1914. He received a Ph.D. in astrophysics from Princeton under the supervision of Henry Norris Russell. After World War II, he became head of the astrophysics department and began his 50-year devotion to space telescopes. As an expert in plasma, Spitzer invented the stellarator in 1950. This device contained hot plasma within a magnetic field and started the search for fusion power that continues today. In 1965, Spitzer joined NASA to develop space observatories, but that year he triumphed in another field entirely. With his friend Donald Morton, Spitzer became the first to climb Mount Thor, a 5,495-foot peak in the Canadian Arctic. In 1977, his campaigning for a space telescope paid off, and funding was granted to the Hubble Space Telescope. He lived long enough to see his dream become a reality in 1990. Key work: 1946 Astronomical Advantages of an Extraterrestrial Observatory. See also, Beyond the Milky Way Radio Astronomy Studying Distant Stars Gravitational Waves. In context. Key astronomers George Gamow, Ralph Alpher. Before 1939 Hans Bethe describes two ways in which helium can be made from hydrogen in stars. After 1957 Fred Hoyle and colleagues set out 8 processes by which chemical elements can be synthesized from other elements in stars. 1964 German-US physicist Arno Penzias and US astronomer Robert Wilson discover the cosmic microwave background radiation. 1970s The mass of atom-based matter as calculated by Big Bang nucleosynthesis is found to be much less than the observed mass of the universe. This puzzle is largely resolved by suggesting the existence of dark matter. In 1931, Georges Lemaître suggested that the universe originated from the explosion of an initial, extremely dense, primeval atom and has been expanding ever since, now known as the Big Bang theory. However, by the mid-1940s, the theory was in need of additional evidence to sustain its credibility. A Ukrainian physicist named George Gamow began thinking about conditions at the start of the universe as it was proposed by Lemaître. He quickly realized that it would have been unimaginably hot. Matter would have consisted of a frenzy of elementary particles, considered at that time largely to comprise protons, neutrons, and electrons. Temperatures would have been too high for these particles to join up, except very briefly. However, after several seconds of existence, the universe would have expanded and cooled to the point where protons and neutrons might be held together by an interaction called the strong nuclear force, thus creating an array of atomic nuclei. Gamow believed that, after a few initial, seed nuclei had assembled from protons and neutrons, others might have been built up by the successive addition of neutrons, with some decaying to protons. At a later time, all the nuclei might have captured electrons to form the atoms of the chemical elements. Doing the math. Gamow asked an American graduate student, Ralph Alpher, to work out the details of his idea. Alpher and a colleague, Robert Herman, performed extensive mathematical calculations. They found that the right conditions for protons and neutrons to come together existed only for a short window of time of a few minutes. Their calculations showed that most of the universe's neutrons would have ended up combined with protons in an isotope of helium, helium-4. A small number would have become other small atomic nuclei. In addition, there would have been large numbers of free protons left at the end of the process, plus some unstable nuclei, which would have quickly decayed. Their calculations showed that the universe would have consisted of about 25% helium, with the rest mainly hydrogen. The paper that Alpher and Gamow published also argued that other heavier nuclei might have been created in the Big Bang through successive additions of neutrons. Atomic nuclei formed from protons and neutrons in the first minutes of the universe. Most neutrons ended up in helium-4 nuclei. Small amounts of helium-3 and deuterium and tiny amounts of lithium-7 were also made. Another isotope of hydrogen, tritium, formed and decayed to helium-3. Energy was released in the form of gamma rays. Correct predictions. It was eventually recognized through the work of scientists such as Fred Hoyle that heavier elements such as carbon were created in stars and supernova explosions. Nevertheless, the Alfvér-Gamow theory correctly explained the relative abundances of hydrogen and helium, lending considerable support to the theory that the universe began with a Big Bang. It also correctly predicted the existence of the cosmic background radiation that was discovered in 1964. George Gamow. George Gamow was born in Odessa, Ukraine, in 1904. From 1923, he attended the University of Leningrad, studying under Alexander Friedmann. In 1928, Gamow briefly stayed at the University of Göttingen in Germany, where he developed a theory called quantum tunneling. This theory was used by others to explain how the fusion of light atomic nuclei might create energy inside stars. In 1933, he defected from the Soviet Union while attending a conference in Brussels. At George Washington University in the US, he turned his attention to the evolution of stars. From 1954, Gamow became interested in genetics and biochemistry. He also wrote a number of popular science books and sci-fi novels. Key works. 1948 The Origin of Chemical Elements. 1952 The Creation of the Universe. See also, The Birth of the Universe, Energy Generation, Nucleosynthesis. In context. Key astronomer Fred Hoyle. Before 1928 George Gamow constructs a formula based on quantum theory that can be used to determine how various atomic nuclei join. 1929 Welsh astronomer Robert Atkinson and Dutch physicist Frits Houtermans figure out how, at the temperatures inside stars, nuclei of light elements could join up, while at the same time releasing energy. After 1979 scientists discover that almost all nuclei of the light elements lithium, beryllium, and boron in the universe are made by the impact of cosmic rays on other nuclei in space, and not in stars. Until the late 1940s, it was not known where the atoms of most chemical elements in the universe, for example, carbon, oxygen, and iron, had come from, nor how they had been made. It had been established in the 1920s that the two lightest elements, hydrogen and helium, made up most of the universe's matter, and in 1948, George Gamow and Ralph Alfvér showed how all of the hydrogen, most of the helium, and tiny amounts of lithium could have been made in the Big Bang. However, the origin of other elements was a mystery. Building to iron. The discovery of their origin was made largely thanks to the work of British astronomer Fred Hoyle. Starting from chance conversations with leading astronomers in the US during an academic tour in 1944, he developed an idea that most chemical elements might be created step by step by nuclear reactions in stars, a process called nucleosynthesis. Hans Bethe had already shown in 1939 that hydrogen could combine to make helium in star cores, but Bethe offered no suggestions for how heavier elements such as iron and carbon could form. The cores of stars were not considered hot enough for such elements to form through nuclear fusion processes. Hoyle, however, thought there could be processes that would sufficiently raise the core temperature of a large enough star. In 1946, Hoyle showed that in the cores of massive stars where the temperature soars to billions of degrees, heavier elements could be made in circumstances called nuclear thermal equilibrium. Such a star would eventually explode as a supernova and eject its heavy elements. In 1954, Hoyle went on to describe how in a massive star that has exhausted its hydrogen fuel, its core would contract and heat up before exploding, and helium atoms would start fusing to create carbon. At the end of this phase, carbon atoms would fuse to create heavier, more stable elements. This could account for the creation of several elements up to iron, which has the most stable of all atomic nuclei. Building nuclei heavier than iron would be more problematic, since it is an energy-consuming process, whereas creating elements lighter than iron releases energy. Hoyle showed how in high-mass stars several elements ranging in mass from carbon to iron could be created by fusion reactions occurring at the same time in shells around the core of the star. the number of shells would increase as the star aged. This diagram shows shells with element-building reactions in an aging red supergiant. Further developments. There was a flaw in Hoyle's stellar element-building scheme, however. A key step known as the triple alpha process, in which 3 helium nuclei fuse to make carbon, appeared to be too slow. Hoyle insisted that there must be a mechanism allowing it to happen at a faster speed and, in 1953, a certain property of carbon was discovered that explained it. Hoyle also explored other processes by which many more elements might be forged in stars. Some of these processes could only occur in the violence of a supernova explosion at the end of a giant star's life. Hoyle's work thus explained not only where chemical elements came from but also how they came to be dispersed throughout the universe. Fred Hoyle. Fred Hoyle was born in Yorkshire, England, in 1915. He attended the University of Cambridge from 1933, gaining a degree in mathematics. During World War II, he worked on radar systems for the British Admiralty. In 1957, Hoyle joined the staff of the Hale Observatories in California and the following year became professor of astrophysics at Cambridge University. Aside from his work on the origin of elements in stars, Hoyle is best known as a proponent of the steady-state theory. This claims that as the universe expands, its average density is kept constant as new matter is continuously created. Ironically, Hoyle coined the phrase, Big Bang, for the main rival theory, during a popular radio talk show. From the 1960s, the steady-state theory fell out of favor. In later life, he took particular interest in the presence of organic molecules in comets, which he believed had brought life to Earth. Key works. 1946 The synthesis of the elements from hydrogen. 1950 The nature of the universe. See also, energy generation. The primeval atom. In context. Key astronomer Bart Bok. Before 1927 American astronomer Edward Barnard catalogues 350 mysterious dark nebulae. 1941 Lyman Spitzer Jr. proposes that stars form from interstellar matter. After 1980s Herbig-Haro objects are identified as jets of plasma released by very young stars within star-forming regions. 1993 high-frequency radio astronomers observe protostars in Bok globules. 2010 The Spitzer Space Telescope takes infrared images of the interiors of 32 Bok globules. The images show warm cores to 26 of the globules and evidence that multiple stars are forming within about 2/3 of them, each star at a different stage in its formation. Bart Bok was an unusual observational astronomer. He made his career studying not that which he could see, but that which he could not. In the 1940s, while observing bright nebulae for evidence of star formation, Bok noticed many small regions that were completely dark. They were surrounded by stars but appeared to be empty holes in space. In 1947, in collaboration with U.S. astronomer Edith Reilly, Bok proposed that these bodies were dense clouds of gas and dust that were in the process of collapsing under their own gravity, and that a new star was forming inside. The dust, formed from specks of silica, water ice, and frozen gases, was dense enough to block out the light of surrounding stars. As a result, no light came out of the cloud, and the light from any stars behind the cloud could not pass through. Bok and Reilly likened these clouds to a caterpillar's cocoon, from which a new, brilliant star would one day emerge. The caterpillar Bok globule in the Carina Nebula is shown here in a photograph from the Hubble Space Telescope. Stars are forming behind the dense veils of dust and gas. Dark nebula. The dense clouds became known as Bok globules. In visible light, they appeared only as a silhouette against the backdrop of stars, with a little light passing through their diffuse outer edges, and for many years it was difficult to observe them in any great detail. This meant that Bok and Reilly's proposal remained hypothetical for several decades. By the 1990s, however, a few years after Bok's death, infrared and radio astronomy were able to peer inside the dusty cloud and pick out areas of heat. These areas indicated that Bok's hypothesis was right, stars were indeed forming within. Bok globules are now seen as a small and dense type of dark molecular cloud, mostly found in the spiral arms of the Milky Way. They are about 1 light-year wide and found in H2 regions, vast interstellar spaces filled with low-density ionized hydrogen atoms. H2 regions form when the ultraviolet emissions of supergiant blue stars ionize the surrounding medium, stripping atoms of their electrons to create positively charged ions. Cold cloud. Bok globules weigh about 50 times the mass of the Sun. They mostly comprise molecular hydrogen, but about 1% is dust. The dust comprises particles made of multiple molecules, and is highly concentrated. The obscuring effect of the dust prevents heat from penetrating the globule, and the temperatures inside are among the coldest measured in the universe, about 10 Kelvin. The outward pressure of the cold gas is weaker than the inward pull of gravity, and a shockwave from a nearby supernova can make the cold clouds collapse. They then become denser and denser until a hot stellar core forms. Bart Bok. Bart Bok. Bartholomeus Jan Bok was born near Amsterdam in 1906. His interest in astronomy began in scout camps, where he was able to observe the stars in clear skies away from the city. Bok began his academic career at 2 Dutch universities, first at Leiden and then, as a Ph.D. student, at Groningen. In 1929, he opted to transfer his studies to Harvard and work under the supervision of Harlow Shapley. He had fallen in love with Priscilla Fairfield, one of Shapley's researchers, and married her 2 days after arriving in the U.S. The pair worked closely together from then on, although Shapley only paid Bok, now going by the Americanized name of Bart. The Boks worked at Harvard for 30 years before they were invited to set up an observatory in Canberra, Australia, in 1957. In 1966, they returned to the U.S. to run observatories in the Southwest. Priscilla died in 1975. Bart continued working until his death in 1983. Key work. 1941 The Milky Way. See also, Space telescopes inside giant molecular clouds and Bartsumian. Introduction. The launch in 1957 by the Soviet Union of the first artificial Earth satellite, Sputnik 1, was a turning point in history, both politically and scientifically. Politically, it provoked the space race, a battle for supremacy in space between the Soviet Union and the United States. Scientifically, it opened up new possibilities for astronomy. Telescopes could be put into orbit, giving them a view unhindered by Earth's atmosphere. Robotic explorers could be sent into the solar system to study planets and other bodies from close quarters. NASA's Mariner 2, the first successful mission to another planet, was launched toward Venus in 1962. Meanwhile, ambitious projects to send people into space carried on. In 1961, Soviet cosmonaut Yuri Gagarin became the first man to orbit Earth. Just 8 years later, the Americans succeeded in putting men on the moon. They would bring pieces of our satellite back with them, which would shed new light on the formation of the early solar system. Seeing from space. Until the mid-20th century, astronomers peered through the narrowest of atmospheric windows, looking only at visible light. Earth's atmosphere is transparent to only 2 parts of the electromagnetic spectrum, the narrow waveband we call visible light and the radio band. Astronomers had no means of knowing about the intense output of ultraviolet, X- and gamma rays from hot, high-energy cosmic sources, which are absorbed by Earth's atmosphere. Cool and concealed constituents of the universe, such as infant stars, were also lurking, waiting for their infrared radiation to be detected. Radio astronomy. The main kind of invisible astronomy open to ground-based observers is radio astronomy. After tentative beginnings in the 1930s, the field developed rapidly in the 1950s. Scientists who had worked in radio science during World War II were instrumental in founding astronomy research groups, such as those at Cambridge and Manchester in the United Kingdom. Also around that time, astronomers at Harvard in the United States identified radio emissions from the hydrogen gas that pervades interstellar space. This discovery allowed the spiral structure of our galaxy Tobe mapped for the first time. In the 1960s, radio astronomers discovered the new phenomena of quasars and pulsars. We now know that quasi-stellar radio sources, or quasars for short, are distant. Galaxies, which have at their heart an immense black hole producing prodigious amounts of energy. Pulsars are neutron stars, bizarre balls of compacted matter, spinning at high speed. Their discovery confirmed theoretical predictions made decades earlier. All windows wide open. By the early 1970s, the first orbiting observatories were operational, and exploring the ultraviolet, X- and gamma rays in the skies. Several series of satellites had been launched under programs such as the Small Astronomy Satellites and Orbiting Astronomical Observatories. These included the 1970 SAS-1 for X-ray astronomy and OAO-3. Infrared astronomy from orbit took longer to achieve because the telescope must be kept very cold, but the first surveys of the infrared sky were undertaken from the ground. All parts of the electromagnetic spectrum were now open to investigation, and the hunt was even on for the elusive particles known as neutrinos. Other worlds in the solar system had become the targets for future missions. Within 3 decades, new technology had transformed astronomers' outlook on the universe. It's highly unlikely there are 2 lots of little green men, on opposite sides of the universe, both deciding to signal to a rather inconspicuous planet Earth. Jocelyn Bell Burnell. In context. Key astronomer Jan Oort. Before 1705 Edmund Halley correctly predicts the return of a comet. 1932 Estonian astronomer Ernst Öpik proposes that long-period comets originate in an orbiting cloud at the edge of the solar system. 1943 Kenneth Edgeworth suggests that the solar system beyond the orbit of Neptune is occupied by many small bodies, some of which become comets. 1950 Fred Whipple proposes that comets are a conglomerate of ices and rocky material. After 1992 David Jewett and Jane Liu discover the first Kuiper belt object other than Pluto. 2014 the Philae lander of the Rosetta spacecraft lands on the comet 67P Churyumov-Gerasimenko. In 1950, reviving a theory proposed by Estonian astrophysicist Ernst Öpik, a Dutch astronomer named Jan Oort argued that there is a reservoir of comets at the edge of the solar system. At the time, it was known that 2 main classes of comets visit the inner solar system, the region comprising the 4 rocky planets. Short-period comets visit at intervals of less than 200 years, and orbit in the plane in which the planets lie. Long-period comets visit at intervals that are longer than 200 years and have orbits inclined at all directions and angles to the plane of the solar system. The origin of either class was subject to speculation. Long-period comets. Oort's idea provided a solution to the origin of long-period comets. A comet periodically visiting the inner solar system will eventually collide with the Sun or a planet, or will be ejected from the solar system after its orbit is disturbed by passing near a planet. This means that comets cannot simply have been going around in their orbits since the solar system formed. Oort suggested that long-period comets passing into the inner solar system are just a small subset of all the comets orbiting the Sun. The comets seen from Earth have been nudged out of the distant comet reservoir, perhaps by a passing star, and have plummeted toward the Sun, taking up long, elliptical orbits. Spherical cloud. Examining the orbits of numerous long-period comets and the farthest distance from the Sun they reach, Oort reasoned that the reservoir for the long-period comets is a shell-like, spherical region ranging up to a maximum of about 4.5–19 trillion miles from the Sun. This region, envisaged to contain billions or trillions of comets, is now known as the Oort cloud. However, it has since been established that short-period comets probably originate from a disk-like region much closer to the Sun, the Kuiper belt. See also, Halley's comet. The Kuiper belt. The composition of comets exploring beyond Neptune. In context. Key astronomer Fred Whipple. Before 1680 German astronomer Gottfried Kirch is the first to find a comet using a telescope. 1705 Edmund Halley shows that the comet of 1682 is the same object as the comets of 1531 and 1607. After 2003 a survey by the Astrophysical Journal finds that over 50 years Whipple's 1950 and 1951 papers were the most cited papers in astronomy. 2014 Rosetta completes a rendezvous with Comet 67P Churyumov-Gerasimenko and successfully sends the Philae lander onto its surface. 2015 new research suggests comets are like deep-fried ice cream, with an icy crust, a colder and more porous inside, and a topping of organic compounds. The arrival of a comet can be a spectacular event, with the brightest of them remaining visible even during the day. Yet U.S. astronomer Fred Whipple showed that these dazzling astral visitors are, in fact, extremely dark objects. In 1950, Whipple proposed that comet nuclei, the bodies of these early solar system remnants, as opposed to the bright, gassy tails visible from Earth, are a rough mix of meteoric materials and volatile ices. The ices are mainly frozen water, along with frozen gases such as carbon dioxide, carbon monoxide, methane, and ammonia. The rest is rock and dust. A black crust of tarry organic compounds, similar to crude oil, coats the surface. Comet nuclei are among the darkest objects in the solar system. Only 4% of the light that falls on them is reflected. Fresh black asphalt, by comparison, reflects nearly twice as much. Whipple's icy conglomerates concept explained how comets could repeatedly send out trails of vapor as they passed the sun. The idea was accepted, albeit with the catchier name, dirty snowballs. However, Whipple had to wait until 1986 for his ideas to be confirmed. That year, the Giotto spacecraft drew alongside Halley's comet, and took close-range pictures of the dark nucleus usually hidden by the bright coma. Images from the Giotto spacecraft revealed the nucleus of Halley's comet to be a dark peanut-shaped body, ejecting two bright jets of material. See also, Halley's comet asteroids and meteorites astrophotography, the Kuiper belt. In context. Key astronomer Sergei Korolev. Before 1955, the U.S. announces plans to launch a satellite for the International Geophysical Year. 1955, 57 Wernher von Braun, a former Nazi rocket scientist recruited by the U.S., launches the Jupiter C rocket, capable of carrying a satellite into orbit. After 1957, on board Sputnik 2, the dog Laika becomes the first large animal in space. 1958, Juno 1 launches the first U.S. satellite, Explorer 1. 1961, Yuri Gagarin orbits Earth in Vostok 1. 1963, Valentina Tereshkova becomes the first woman and first civilian in space. 1965, Voskhod 2 becomes the first two-man crew in space. Alexei Leonov completes the first spacewalk. With the launch of Sputnik 1, the world's first artificial satellite in 1957, the Soviet Union won the first round in the superpower space race. This momentous accomplishment was achieved primarily through the drive and genius of one man, the tough and pragmatic chief designer, Sergei Korolev, the scientist who masterminded the top-secret space program. Until the collapse of the Soviet Union in 1991, very little was known about Korolev in the West. The Soviets had referred to him only as chief designer for fear that the Americans might try to assassinate him. Korolev had trained as an aircraft designer, but his true talent lay in strategically planning vast and complex projects under extreme political pressure. By 1957, he already had one major first under his belt, with the launch of the world's first intercontinental ballistic missile in 1953. During an extraordinarily successful career, he would go on to have several more, each time catching the U.S. by surprise. In 1957, Korolev launched a dog, Laika, into orbit, which prepared the way for the first man in space in 1961, and the first woman in 1963. 2 years later, this was followed by the first two-man crew and first spacewalk. The time will come when a spacecraft carrying human beings will leave the Earth and set out on a voyage to distant planets, to remote worlds. Sergei Korolev. Vostok 1, designed by Korolev, launched Yuri Gagarin from the Baikonur Cosmodrome on April 12, 1961. During the flight, Gagarin said, "I don't see any God up here." The space race. However, it was the launch of Sputnik 1 on October 4, 1957, that was to have the biggest impact on American public opinion. Russia was routinely caricatured in the U.S. media as a backward country, but the launch of Sputnik was undeniable evidence of Soviet technological superiority and soon stoked Cold War paranoia. The orbiting Red Moon raised the possibility of nuclear bombs raining down on American cities, and the fears it aroused were seized upon by political opponents of U.S. President Eisenhower. When the Soviets put the first man in space in 1961, NASA's press officer, woken by a 4:30 a.m. call, said, "We're all asleep down here." The next day's headline read, "Soviets put man in space. Spokesman says U.S. asleep." The perceived technological gap kick-started the U.S. space program and resulted in the Apollo missions. With Korolev's sudden death in 1966, the Soviets' winning streak ended. Their space program had lost the magnetic personality that held a vast, complex enterprise together, and became embroiled in politics and bureaucracy. It is intriguing to wonder whether the Soviet Union might have put the first man on the moon with Korolev at the helm. Instead, the U.S. gained the initiative and achieved that goal in July 1969. Sputnik 1 was a relatively simple craft, comprising a metal sphere containing radio, batteries, and a thermometer. Its psychological impact on the U.S. was immense. Sergei Korolev. Born in 1906, Sergei Pavlovich Korolev studied under the aircraft design pioneer Andrei Tupolev, becoming the chief engineer at Russia's Jet Propulsion Research Institute by the mid-1930s. In 1938, however, he was a victim of Stalin's purges. Denounced by his colleagues, Korolev was tortured and sent to the Gulag in eastern Siberia, where he worked in a gold mine and contracted scurvy. Released in 1944, he was appointed head of the secret Scientific Research Institute No. 88, the Soviet space program. Korolev won political favor with his idea for Sputnik 1, a heavier artificial satellite than the Americans were capable of launching at the time. Larger than life, Korolev had a roaring temper and was prone to shouting expletives. But, despite his bear-like frame and limitless energy, he was weaker than he appeared. Korolev had suffered a heart attack in the Gulag. He could not turn his neck and his jaw had been broken so badly that it hurt for him to laugh. He died during routine colon surgery in 1966. See also, the space race exploring the solar system, exploring Mars. In context. Key astronomers. Giuseppe Cacconi, Philip Morrison. Before 1924, a National Radio Silence Day is instigated to tune in on any potential Martian messages. 1951, U.S. physicists Harold Ewan and E. M. Purcell detect the 21 cm hydrogen line. After 1961, Frank Drake formulates the Drake equation to estimate how many intelligent civilizations are likely to lie beyond the solar system. 1977, at Ohio University, Jerry Emmond picks up a sharp signal 30 times the background noise level. This wow signal has never been detected again. 1999, the SETI at Home network uses the combined power of millions of volunteer desktop computers. In September 1959, the scientific journal Nature carried a short but hugely influential article, Giuseppe Cacconi and Philip Morrison's Searching for Interstellar Communications. This introduced an entirely new field of scientific endeavor, speculation on the nature of extraterrestrial life and the possibility of intelligent beings existing outside of Earth. For the first time in scientific history, alien hunting had been framed as a serious proposition. The completion, in 1957, of the 250-foot Mk1 radio telescope at Jodrell Bank in England, just in time to track the world's first artificial satellite, Sputnik 1, had brought new possibilities into focus. If equipped with a powerful transmitter, this kind of telescope was capable of communicating across interstellar distances with any civilization that had managed to achieve the corresponding technology. Cacconi and Morrison's paper argued that, on some planet orbiting a distant star, advanced societies may already be trying to make contact. The pair suggested looking for signals in the microwave spectrum, identifying likely frequencies and even potential places to start the search for intelligent life. A place to look. Cacconi and Morrison focused on the 21 cm line, a radiation emission line of a hydrogen atom. In the high-frequency radio band, This 1420 MHz radiation is emitted when protons and electrons within a hydrogen atom change their energy state. Its discovery, in 1951, allowed the distribution of hydrogen across the galaxy to be mapped using radio waves, which, unlike visible light, are not blocked by dust clouds. Since this line is universal, Cocconi and Morrison argued that it would be known to all intelligent civilizations, and that any search should begin by looking for transmissions around this frequency band. They predicted the most likely form of transmission, a pulse-width modulated wave, like an FM radio signal, on a loop like a Mayday callout. The modulated wave would carry a constant amplitude but produce regular pulses of higher frequency. A signal might cycle over long periods, perhaps a number of years. Modulation is a method by which information can be transmitted within a wave signal. The amplitude is kept constant, while the frequency varies. Future searches. Cocconi and Morrison's ideas dominated the search for extraterrestrial intelligence for decades. Acting on the article's recommendations, Frank Drake's pioneering 1960 experiment Project Ozma, at the Green Bank Observatory in West Virginia, targeted the close sun-like stars Tau Ceti and Epsilon Eridani, scanning around the 21 cm line. Sadly, the project failed to find any convincing candidates. Today, many question the wisdom of such limited searches. Instead, SETI researchers look for the chemical or thermal signatures of advanced civilizations, leakage from signals not intended for US, and novel methods of communication using lasers or neutrinos. The Lovell Radio Telescope at Jodrell Bank, the third largest radio telescope in the world, was used as part of the Project Phoenix SETI program in the 1990s and 2000s. Giuseppe Cocconi and Philip Morrison. Giuseppe Cocconi was born in Como, Italy, in 1914. After World War II, he joined Cornell University, New York. Working with his wife, Vanna, Cocconi demonstrated the galactic and extragalactic origins of cosmic rays. Later, he became director of research at CERN in Geneva. Philip Morrison studied at the University of California, Berkeley, under Robert Oppenheimer. During World War II, he worked on the Manhattan Project to build the first atomic bomb, and famously shared a car with the core of the Trinity bomb as it was transported to the test site. He later became a vocal anti-nuclear campaigner. He was a great popularizer of science and narrated the 1977 documentary Powers of 10. Key work. 1959 Searching for Interstellar Communications. See also, Life on Other Planets, Exoplanets. In context. Key astronomer. Eugene Shoemaker. Before 1891 American geologist Grove Gilbert suggests that the Moon's craters are the result of meteorite impacts. 1891 mineralogist Albert E. Foote produces the first geological description of the crater. After 1980 American physicist Luis Alvarez proposes that a worldwide stratum of shocked quartz between the Cretaceous and Tertiary periods indicates a huge impact, which led to the mass extinction of dinosaurs. 1994 Comet Shoemaker-Levy, co-discovered by Eugene Shoemaker, impacts Jupiter and is observed by the Galileo spacecraft en route to the planet. So great was the contribution of American geologist Eugene Shoemaker to planetary science that he is the only person whose ashes have been sent to the Moon. He was a founding figure of astrogeology, a science that uses the techniques of geology to investigate alien worlds. Shoemaker's early work hinged on a crater in the Arizona desert known as Meteor Crater. Early European settlers in nearby Canyon Diablo believed it to be the vent of an ancient volcano. Railroad engineers passing through in the 1880s found large iron-rich rocks strewn across the desert, which suggested the crater was caused by the impact of a metallic meteorite. However, this was dismissed because the volume of debris around the rim largely matched the volume of the crater itself. It could not be a meteor crater if there was no meteorite. In 1903, Daniel Barringer, a mining engineer, searched for the iron meteor under the crater floor, but to no avail. Not until 1960 did Shoemaker find the evidence. The crater contains shocked silica only seen previously at nuclear bomb test sites. These minerals cannot have been made naturally by volcanic forces, only the energy of a meteorite traveling at 40,000 miles per hour could have done it. That energy had vaporized the meteorite, which explained why it was missing. Shoemaker had provided the first proof that large meteorites strike Earth, opening up new possibilities for investigating extraterrestrial objects. Not going to the moon and banging on it with my own hammer has been the biggest disappointment in life. Eugene Shoemaker. See also, Asteroids and Meteorites, the discovery of series, the composition of comets. In context. Key astronomer. Robert Leighton. Before 1954, Canadian astronomer Harry Hemley Plaskett observes the Sun's oscillation effect. After 1970, American physicist Roger Ulrich proposes that the oscillations are from acoustic waves in the solar interior. 1970s, helioseismology opens up a new way of investigating the interior of the Sun. 1995, the Solar Observatory satellite SOHO is launched. 1997, the SOHO team discover jet streams of plasma in the convective zone. 1990, 2000s, hundreds of thousands of the Sun's vibrational modes are identified. 2009, the Kepler satellite measures oscillations in Sun-like stars to describe conditions on exoplanets. In 1960, American physicist Robert Leighton made observations with a camera that he had devised, which led to the discovery that the Sun is ringing like a bell, as he put it. Working with Robert Noyes and George Simons, Leighton picked up perturbations of the Sun's surface using Doppler shift solar cameras. These cameras detected tiny shifts in the frequency of the Sun's absorption spectra as its outer layer moved toward or away from Earth. 5-minute oscillations. The complex patterns of vibrations, with an average period of 5 minutes, were at first thought to be a surface phenomenon. Then in 1970, Roger Ulrich explained them as trapped acoustic waves bouncing within the Sun from one side to the other, causing the star's surface to wobble as it resonated. Today, these waves allow scientists to investigate the interior of the Sun, in much the same way that acoustic earthquake waves reveal the inner composition and structure of Earth. Known as helioseismology, this process is often compared to trying to build a piano by studying the sounds it makes when it falls down a flight of stairs, but it has produced a model of the Sun's interior processes. The model places tight constraints on the amount of helium in the star's core, which has important consequences for models of the early universe. With his very inquisitive mind, every funny effect that you'd see in nature he'd try to explain. Jerry Neugebauer, physicist and colleague of Robert Leighton. See also, the properties of sunspots, the Homestake experiment, exoplanets. In context. Key astronomer Riccardo Giacconi. Before 1895, German physicist Wilhelm Röntgen discovers high-energy radiation, which he names X-rays. 1949, solar X-rays are first detected by sounding rockets. After 1964, Cygnus X-1, the first confirmed black hole binary system, is discovered. 1966, X-rays are detected from galaxy cluster M87, in the Virgo cluster. 1970, Uhuru, the first dedicated X-ray mission, is launched. 1979, X-rays from Jupiter are detected by the Einstein Observatory. 1999, the Chandra X-ray Observatory is launched. X-rays are a form of high-energy, electromagnetic radiation released by extremely hot objects. In the early 20th century, astronomers realized that space should be flooded with X-rays from the Sun. Moreover, the Sun's X-ray spectrum would reveal a lot about the processes at work within the star. However, X-ray astronomy was not possible until the advent of rockets and satellites. Despite their energy, X-rays are easily absorbed, which is why they are so good at imaging the body. Water vapor in Earth's atmosphere effectively blocks X-rays from reaching the surface, a good thing for life, because high-energy X-rays can cause damage and mutations when they impact on soft, living cells. The first glimpse of the Sun's X-rays came in the late 1940s, during a U.S. Naval Research Laboratory program to study Earth's upper atmosphere. A team led by U.S. rocket scientist Herbert Friedman fired German V-2 rockets into space equipped with X-ray detectors, essentially modified Geiger counters. These experiments provided the first incontrovertible evidence of X-rays from the Sun. By 1960, researchers were using aerobee-sounding rockets to detect X-rays, and the first X-ray photos of the Sun were taken from an aerobee high. 2 years later, the first cosmic X-ray source was detected. Nothing is going to happen unless you work with your life's blood. Riccardo Giacconi. Extrasolar X-rays. Riccardo Giacconi, an Italian astrophysicist then working for American Science and Engineering, had successfully petitioned NASA to fund his team's X-ray experiment. The team's first rocket misfired in 1960, but by 1961 it had a new, improved experiment ready for launch. This instrument was 100 times more sensitive than any flown to date. Using a large field of view, the team hoped to observe other X-ray sources in the sky. Success followed a year later. The rocket aimed its camera first at the moon and then away from it. What the camera saw came as a complete surprise to the team. The instrument detected the X-ray background, a diffuse signal coming from all directions, and a strong peak of radiation in the direction of the galactic center. Stars like the Sun emit about 1 million times more photons at visible light frequencies than they do as X-rays. The source of the X-ray signals, by contrast, radiated 1,000 times more X-rays than light. Although a small, barely visible point in the sky, the source was pumping out 1,000 times more X-rays than the Sun. Furthermore, certain physical processes were taking place within the source and these had never been seen in the laboratory. After weeks of analysis, the team concluded that this must be a new class of stellar object. Search for the source. There was no candidate in the solar system to account for the intense radiation. The most likely source was named Scorpius X-1 after the constellation within which it was located. Herb Friedman at the NRL confirmed the result using a detector with a larger area and better resolution than the A-SAND instrument. SCO X-1 is now known to be a double star system and is the brightest, most persistent X-ray source in the skies. Further launches revealed a sky dotted with X-ray sources, both galactic and extragalactic. In a short space of time, the team had detected a disparate set of celestial oddities emitting X-rays. These included supernova remnants, binary stars, and black holes. Today, more than 100,000 X-ray sources are known. The Chandra X-ray Observatory was launched by NASA in 1999. It was initially planned to operate for 5 years, but was still in use in 2016. Toward Chandra. By the mid-1960s, instruments were becoming ever more sensitive. Detectors were able to record X-rays 1,000 times weaker than SCO X-1 just 5 years after Giacconi's discovery. Initially proposed by Giacconi in 1963, Uhuru, the first satellite dedicated solely to X-ray astronomy, was launched in 1970. It spent 3 years mapping X-rays. This all-sky survey located 300 sources, including a bizarre object in the center of the Andromeda Galaxy, and it earmarked CYG X-1 as a potential black hole. Uhuru also found that the gaps in galaxy clusters are strong sources of X-rays. These apparently empty regions are in fact filled by a low-density gas at millions of degrees Kelvin. Although thinly spread, this intercluster medium contains more mass than that of all of the cluster's galaxies combined. In 1977, NASA launched its High-Energy Astronomy Observatory program. HEAO-2, renamed the Einstein Observatory, was equipped with highly sensitive detectors and revolutionized X-ray astronomy. With its fused quartz mirrors, the telescope was 1 million times more sensitive than that of Giacconi's 1961 Discovery rocket. Einstein observed X-rays emanating from stars and galaxies, and even from planetary aurorae on Jupiter. Eager to probe the X-ray background further, Giacconi once again proposed an advanced telescope. In 1999, this became the Chandra X-ray Observatory, the third of the orbiting great observatories. Chandra is the most powerful X-ray telescope ever built, tens of billions of times more sensitive than the early detectors. Its phenomenal performance outstripped all expectations and its mission lifetime was tripled from 5 to 15 years. As of 2016, however, its mission is ongoing. Chandra's outstanding technical firsts include detecting sound waves coming from a supermassive black hole. The X-ray data, when Combined with optical observations from the Hubble Space Telescope and infrared data from the Spitzer Space Telescope, have provided stunning images of the cosmos. Active regions of the Sun are revealed by combining observations from many telescopes. High-energy X-rays are shown in blue, low-energy X-rays green. Realm of the X-rays. X-ray astronomy observes the highest energy objects in space, colliding galaxies, black holes, neutron stars, and supernovae. The energy source behind this activity is gravity. As matter falls toward a massive concentration of material, particles collide and accumulate. They give up their energy by emitting photons, which at these speeds have X-ray wavelengths, equivalent to temperatures of tens of millions of degrees. The same mechanism is at work in a wide range of dramatic phenomena. Active stars more massive than the Sun, for example, produce strong solar winds and significant amounts of X-rays. X-ray binary star systems, in which mass transfers from one star to its partner, also produce intense radiation. The universe is popping all over the place. Riccardo Giacconi. Seeing black holes. When stars explode at the end of their lives, the blast waves from the supernova compress the interstellar medium, causing the gas to release X-rays. Left within what remains of the supernova, the massive star continues life as a neutron star or a black hole. Turbulence generated by material being torn apart as it is sucked into a black hole will also produce X-rays. The radiation being pumped out causes the outer layers of the supernova remnant to fluoresce in a range of colors. Certain galaxies have centers that outshine all the billions of stars in the galaxy itself, with emissions that are bright at all wavelengths. The center of such an active galactic nucleus is assumed to contain a supermassive black hole. Material falling toward the centers of galaxy clusters, the largest structures in the universe, also shines in X-rays, and is not visible in other light frequencies. Chandra has now taken 2 deep-field images of the X-ray background, 23 and 11-day exposures of the northern and southern hemispheres of the sky. X-ray instruments of the future may help scientists see how black holes are distributed. Observations in the X-ray spectrum reveal hidden structures. The larger blobs in this patch of sky from an ESA X-ray survey are galaxy clusters, smaller dots are black holes. Riccardo Giacconi. Born in Genoa, Italy, in 1931, Riccardo Giacconi lived in Milan with his mother, a mathematics and physics high school teacher. She instilled a love of geometry in the young Riccardo. Giacconi's first degree was from the University of Milan. With a Fulbright scholarship, he moved to Indiana University in the US, and then to Princeton, to study astrophysics. In 1959, Giacconi joined American Science and Engineering, a small firm in Cambridge, Massachusetts. Sandy built rocket-borne monitoring equipment for measuring electrons and artificial gamma-ray bursts from nuclear weapons. Giacconi was tasked with developing instruments for X-ray astronomy. He was at the heart of most of the breakthroughs in X-ray astronomy, and in 2002, he was awarded a share of the Nobel Prize in Physics for his contributions to astrophysics. In 2016, he was still working in his mid-80s, as principal investigator for the Chandra Deep Field South project. See also, the Homestake experiment discovering black holes. In context. Key astronomer Martin Schmidt. Before 1935, Karl Jansky develops the first radio telescope. 1937, radio engineer Grote Reber makes the first radio survey of the sky. 1955, the Radio Astronomy Group at Cambridge begins to map the northern hemisphere at 159 MHz. After 1967, Jocelyn Bell Burnell, of the Radio Astronomy Group, detects the first pulsars. 1972, the first physical, rather than theoretical, candidate for a black hole is identified in the Cygnus X-1 system. 1998, Andrea Ghez detects a black hole 4 million times as massive as the Sun at the center of the Milky Way. By the end of the 1950s, radio astronomy had given a new way to look to the sky. In addition to imaging celestial objects with light, surveys of the sky could use radio emissions from space, showing up previously unseen features. Radio waves were found to come from the Sun, the stars, and the center of the Milky Way, but there were also mysterious invisible radio sources. In 1963, Martin Schmidt, a Dutch astronomer working with the Hale telescope at Palomar Observatory, California, managed to catch a glimpse of the light from one of these objects. When he looked at its redshift, he discovered something startling. The object was 2.5 billion light-years away, which meant that it was unimaginably bright. Its absolute magnitude was 26.7. The object in Schmidt's eyepiece was 4 trillion times brighter than the Sun, brighter than the whole of the Milky Way put together. Schmidt named the body a quasi-stellar radio source, which was later shortened to quasar. Before Schmidt, the object had been known as 3C273. The 3C referred to the third Cambridge catalogue of radio sources and 273 because it was the 273rd object to be located in that survey. 3C273 had been spotted in 1959, although the first quasar to be identified was 3C48, which had been found shortly before. Improving radio astronomy. Radio astronomy had started in the 1930s after the accidental discovery of cosmic radio sources by Karl Jansky. Interrupted by World War II, and helped somewhat by the development of radar technology, surveys using radio telescopes did not start in earnest until 1950. Early surveys were hindered by the low frequency of 81.5 MHz used by early radio receivers. At that frequency, it was difficult to pinpoint the location of signals with a low flux density. In 1955, the Radio Astronomy Group at Cambridge University began a survey using a radio interferometer, which picked up signals at 159 MHz. This was better at resolving faint radio sources, and led to the discovery of the first 2 quasars. The light from both objects was invisible to the optical telescopes available to the Cambridge researchers at the time. However, their measurements of the flux density told them that these radio sources were very compact. In 1962, 3C273 was occulted, or covered, several times by the Moon. By watching for the reappearance of the radio source from behind the lunar disk, astronomers were able to get a very precise location of the source. Martin Schmidt used those measurements to take a look at it through the Hale telescope, then the largest optical telescope in the world. He found 3C273 to be the brightest object yet known. He published his findings in Nature in March 1963, and in the same issue, 2 other astronomers, Jesse Greenstein and Thomas Matthews, presented data on the redshift of 3C48, which showed that the object was moving away at 1/3 of the speed of light, making it the fastest moving object yet discovered. By the early 1970s, hundreds of quasars had been identified. Many were even more distant than 3C48 and 3C273. Today, most of the quasars that have been found are located about 12 billion light-years away. In addition, quasars are mostly brighter than the first observations suggested, with luminosities up to 100 times that of the Milky Way. In 2001, the Hubble Space Telescope captured a glimpse of one of the most distant and luminous quasars ever seen. It dates to less than 1 billion years after the Big Bang. Understanding has not developed very much in 50 years. You only see a point source, you don't see its structure. It's a difficult thing to get hold of. Martin Schmidt speaking in 2013. White holes. The debate now began as to what these things actually were. One suggestion was that the enormous redshifts seen in quasars were not the result of the expansion of space, but were the result of the light crawling out of a large gravity well. Such a well would be created by a truly monstrous star, with a gravitational field close to that of a black hole. However, calculations showed that such a star could never be stable. Another proposal was that a quasar was the opening of a white hole. A white hole is the opposite of a black hole. This idea was proposed in 1964, and white holes remain entirely hypothetical. They are generally ignored as a theory today, but in the 1960s and 70s, black holes were also unobserved phenomena, so the concept of white holes carried more weight. The idea is based on a complex interpretation of the Einstein field equations of general relativity, which proposes that a black hole that exists in the future would link to a white hole that exists in the past. A white hole is, therefore, a region of space where light and matter can leave but cannot enter. This would match the focused streams of radiation and matter that were being observed firing out of quasars. The question remained over where all that energy came from. The answer offered was that it has come through a wormhole, or Einstein-Rosen bridge, a theoretical feature of spacetime that connects the future to the past. An artist's impression shows the possible structure of quasar 3C279. A disk of material rotates around a black hole a billion times as massive as the Sun. Small bangs. Currently, the only event that is accepted as anything like a white hole is the Big Bang itself, and some theories suggest that the material entering black holes may emerge in another universe as small bang events. Nevertheless, as the understanding of black holes grew, the white hole explanation of quasars faded away. Twinkle, twinkle, quasistar biggest puzzle from afar, how unlike the other ones, brighter than a billion suns. Twinkle, twinkle, quasistar, how I wonder what you are. George Gamow. Supermassive black hole. Quasars are too luminous and energetic to be using nuclear fusion, the process that powers stars, to produce their energy. However, theoretical work on black holes showed that a region of material, known as the accretion disk, would form around an event horizon. Since this material was steadily pulled into the black hole, it would heat up to millions of degrees. A supermassive black hole, with a mass billions of times greater than the Sun, would produce an accretion disk that matched the output observed in quasars. The accretion disk theory also matched up with the beams of plasma, known as relativistic jets, that blasted out in opposite directions from some quasars. These are caused by the spin of the black hole, which creates a magnetic field and focuses matter and radiation into two streams. Superheated plasma blasts out at close to the speed of light from each stream. Today's understanding of quasars began to crystallize in the 1980s. The accepted view is that a quasar is a supermassive black hole, or perhaps two, at the heart of a galaxy that is eating up the stellar material. A galaxy that behaves like this is said to have an active nucleus, and it appears that quasars are just one manifestation of these so-called active galaxies. An active galaxy is detected as a quasar when the relativistic jets are angled to Earth's line of sight. Therefore, the object is detected chiefly from its radio emissions. If the jets are perpendicular to Earth's line of sight, then they can never really be detected, and instead Earth sees a radio galaxy, a galaxy that is pumping out a loud radio source. If the relativistic jets are directed right at Earth, an excellent view is gained of the active nucleus in an object, known as a blazar. Most quasars are ancient objects, and Earth sees their activity from when the universe was young. Unlike in other active galaxies, the brilliance of a quasar's nucleus makes it hard to discern much of the galaxy around it. It is thought that young galaxies always have active nuclei, and that once there is no material left for their black hole to swallow, they become quieter places, like the Milky Way today. However, galactic collisions, in which one galaxy merges with another, can activate the nucleus again. It is likely that the Milky Way, which is on track to collide with Andromeda in 4 billion years, is destined to become a quasar itself one day. The Hubble telescope took this image of the active galactic nucleus of the elliptical galaxy NGC 4261. The disk of dust is 800 light-years wide. Maarten Schmidt. Born in Groningen, the Netherlands, Maarten Schmidt went to his home city's university and studied alongside Jan Oort. Schmidt earned his doctorate before emigrating to the US and taking up a post at Caltech's Palomar Observatory. He became a leading expert on star formation, encapsulated by the Schmidt law, which relates the density of interstellar gas clouds to the rate of star formation inside them. Schmidt also became one of the chief investigators of quasars. After a conference on the subject in 1964, Schmidt and the other leading figures in the field, including William Fowler and Subramanian Chandrasekhar, were leaving on the same plane, which experienced a dicey takeoff. Fowler is said to have quipped, "If this plane crashes, at least we'll get a new start on this quasar problem." Schmidt went on to occupy several eminent roles in astronomical institutions. Key work. 1963 3C273, a star-like object with large redshift. See also, The theory of relativity, radio astronomy, nuclei and radiation, quasars and pulsars, discovering black holes, the heart of the Milky Way. In context. Key astronomers: Robert H. Dick, James Peebles. Before 1927, Georges Lemaitre proposes his hypothesis of the primeval atom. 1948, Ralph Alpher and Robert Herman predict that radiation from the Big Bang would now have a temperature of 5 K. 1957, Soviet astronomer Tigran Shmayanov reports a radio emission background of 4+3 K, but does not connect this finding with the Big Bang. After 1992, the COBE results confirm blackbody curve and anisotropy of the CMB. 2010, WMAP measures tiny temperature variations of 0.00002 K in the CMB. 2013, the Planck team releases a detailed map of the CMB. The discovery of the universe's first light is one of the most fundamental scientific findings of all time. A full 99.9% of all photons arriving at Earth are associated with this cosmic microwave background. It has been traveling for more than 13 billion years, reaching us from a time near the very dawn of the universe. The CMB is the thermal radiation emitted when the universe was at a temperature of about 4000 K. The scientist who usually takes the credit for the prediction of the CMB is physicist George Gamow. An expanding universe implied a point at which it was once squeezed into a tiny volume. Gamow saw that this in turn implied a hot beginning, and realized that such a hot Big Bang would have left its signature in the sky. In 1948, his doctoral students Ralph Alpher and Robert Herman worked out the details of this fireball radiation. Cooled by the expansion of the universe, over 13 billion years, they deduced that it should take the form today of radiofrequency radiation as if emitted by an object at 3 K, just above absolute zero. Seemingly unaware of Alpher's and Herman's work, Robert H. Dick, working at the Princeton University Rad Lab, independently predicted the CMB in the early 1960s. Dick asked his team of postgraduates to find it. David Wilkinson and Peter Roll were to build a machine to detect it, while James Peebles was to think about the theory. There is no point in attempting a half-hearted experiment with an inadequate apparatus. Robert H. Dick. Robert H. Dick. Bob Dick was born in St. Louis, Missouri, in 1916, but grew up in Rochester, New York. Fascinated by science from a young age, he began an engineering degree before switching to physics. After graduating from Princeton in 1939, Dick worked at MIT's Radiation Laboratory during World War II, developing microwave radar. He and his wife, Anne, returned to Princeton following the war and remained there for the rest of their lives. Dick's research was initially centered around radiation, and he formulated a new quantum theory to explain the emission of coherent radiation produced by a theoretically ideal laser. His interest in radiation led him to team up with James Peebles and predict the existence of the CMB. By the 1960s, Dick's interests had spread to theories of gravitation. He developed high-precision experiments to test general relativity more robustly and produced an alternative theory of gravitation. An imaginative experimentalist and a prolific inventor, Dick held more than 50 patents, ranging from lasers to designs for clothes dryers. Echoes of the Big Bang. Gamow had assumed that the faint signal of the CMB would be indistinguishable from radio waves flooding in from other astronomical objects, but Alpher and Herman showed that it would have two distinguishing features. It would come from every direction in the sky, and the energy curve would have the telltale shape of an object very close to thermal equilibrium, a so-called black body. Alpher and Herman stopped there, advised that the radio telescopes of the day would not be able to pick up such a quiet hiss. But Dick thought otherwise. During World War II, while working on radar systems, he had built such a machine, the Dick radiometer, which collects a microwave signal and measures its power. Dick added a switch to filter out noise. The device is still used today in space telescopes and satellites. Choosing a suitable bandwidth in which to conduct the search for the radiation was the next important stage, since so many things produce radio waves. For example, the sky is filled with microwave wavelengths around the 814th in Mach, emitted by atoms of hydrogen. It seemed logical to start at a dark part of the spectrum. In the spring of 1964, Wilkinson and Roll began looking at the 1/1/4 in band, but they were beaten in their quest by a piece of serendipity. Holmdel Horn. Less than an hour's drive from Princeton University is the Holmdel Horn, a giant radio antenna, built by Bell Laboratories for satellite communications. In 1964, it was being used by two radio astronomers, Robert Wilson and Arno Penzias, who were trying to detect a halo of cold gas around the Milky Way. Penzias and Wilson were looking at the 2/3 in range, but they could not get rid of a stubborn low-level hiss that was ruining their measurements. The pair painstakingly eliminated potential sources of interference, dusting down plugs and checking circuits. At first, they thought that the noise was coming from New York, but pointing their telescope away from the city did not help. Then they thought it might be high-altitude static from a nuclear bomb test or an unknown radio source in the solar system, but, over the course of the year, the signal never varied its ceaseless soft hiss. In desperation, they even removed a nesting pair of pigeons and chipped away an accumulation of white dielectric material. Stumped, Penzias contacted a colleague, who directed him to James Peebles at Princeton. Taking the call for Peebles, Dick knew immediately what the Bell Laboratories scientists had found. He hung up the telephone and said to his colleagues, "Well, boys, we've been scooped. Science is a series of successive approximations." James Peebles. A theoretical black body absorbs all the radiation that hits it, then emits radiation at different intensities across different wavelengths, depending on its temperature, as shown here. The only way is up. The discovery of the cosmic background radiation is one of the three experimental pillars of the Big Bang theory, the other two being Hubble's law and the cosmic abundances of the elements hydrogen and helium. Big Bang theorists had predicted exactly what had now been found, radiation coming from all directions at 3K. The Big Bang had until then been a highly contested idea, and many scientists, including Penzias and Wilson, still favored Fred Hoyle's steady-state model, in which an expanding universe essentially remains unchanging due to the constant creation of matter. According to this theory, the universe does not change in appearance over time. Steady-state theorists suggested that the microwave background was the result of scattered starlight from distant galaxies. To demonstrate to a skeptical physics community that the signals were indeed the relic fireball radiation predicted by Big Bang theory, it was necessary to confirm Alfors and Hermann's condition that the radiation should match that of a theoretical black body. This required measuring the CMB at different frequencies. The next obvious move was to take an even more accurate determination of the spectrum by launching a space-based receiver. During the 1970s and 1980s, Herb Gush, a physicist at the University of British Columbia, fired sounding rockets into space in order to observe the CMB without interference from Earth's atmosphere. This indicated that the CMB had the blackbody signature of a system in thermal equilibrium, with no heat flowing from one part to another. This astounding, and often overlooked, result verified that the signal was thermal in origin. Unfortunately, the rocket's hot exhaust gases often marred Gush's measurements, preventing him from producing a definitive result. All of our best physical theories are incomplete. James Peebles. Robert Wilson and Arno Penzias pose in front of the Holmdel Horn antenna following the announcement in 1978 of their Nobel Prize for discovering the CMB. Edged out. By 1989, Gush had finally developed an instrument that could compare the CMB spectrum with that of an onboard radiator that approximated a black body. However, problems with a malfunctioning vibrator delayed the launch until early 1990. The results were immediate and striking, but Gush had missed his opportunity for a scoop by a few weeks. NASA's Cosmic Background Explorer satellite, launched in late 1989, already had the shape of the spectrum with a temperature near 2.7 K. In the end, Gush's rocket data confirmed Cobb's results and not the other way around. Peebles was later to state that Gush had deserved a Nobel Prize for his work. Cobb's results returned a near-perfect match with the theoretical blackbody spectrum and revealed, for the first time, a faint unevenness in the background radiation. Subsequent missions, such as NASA's Wilkinson Microwave Anisotropy Probe, launched in 2001, and ESA's Planck spacecraft, launched in 2009, have mapped the CMB's lumpiness in greater detail. The CMB represents the outer shell of the observable universe. Just beyond it lies the moment of the Big Bang, shown here as a series of flashes. James Peebles. Philip James Edwin Peebles was born in 1935 in Winnipeg, Canada. After graduating from the University of Manitoba, he earned a doctorate at Princeton University, where he found himself surrounded by all these people who knew so much more than I. Working under Robert H. Dick, Peebles found he was retreading old paths. He began to focus on the constraints that the CMB put onto the early universe, specifically on the creation of atomic nuclei in the Big Bang and on how small temperature differences affect models of structure formation in the universe. Peebles also made important contributions to theories of dark matter and dark energy. With typical modesty, he says that his cold dark matter model became popular because it was easy to analyze. He is currently Albert Einstein Professor of Science at Princeton. Key works: 1971 Physical Cosmology, 1980 Large-Scale Structure of the Universe, 1993 Principles of Physical Cosmology. See also, The Birth of the Universe Beyond the Milky Way, Cosmic Inflation Observing the CMB. In context. Key astronomer Carl Sagan. Before 1865 German physician Hermann Eberhard Richter suggests that planets could be seeded by simple life carried by comets. After 1973 Brandon Carter sets out an early version of the anthropic principle, which states that the universe is necessarily a certain way, otherwise humans would not be here to experience it. 1977 Voyagers 1 and 2 are launched, carrying images and sounds from Earth. 2009-2016 NASA Space Telescope Kepler discovers 3,443 exoplanets in 2,571 planetary systems. 2015 Kepler discovers the first Earth-sized planet in a habitable zone of another star. The Copernican principle states the working assumption that Earth is not special, it is no more than an average planet, orbiting a medium-sized star, in an unremarkable part of an ordinary galaxy. If Earth is not unique, then there is little reason to think that other planets cannot also harbor life. Given the number of stars in the universe, in the order of 1023, this might be a statistical certainty. Over the centuries, many thinkers, such as American Carl Sagan, have pondered the possibility. Is Earth alone? In the 16th century, the Italian monk Giordano Bruno proposed that the stars were other suns, each of which could have its own solar system. Life could even populate these other Earths. Believing that the universe was infinite, Bruno also insisted that it could have no center. Bruno was tried by the Roman Inquisition for these and other heretical beliefs and burned at the stake in 1600. Throughout history, various astronomers have claimed to see evidence for life on other planets of the solar system. In the 1890s, American astronomer Percival Lowell claimed to have mapped artificial canals on Mars, while the dense clouds of Venus were imagined by Swedish chemist Svante Arrhenius in 1918 to hide from view a lush surface blooming with life. It is now known that the clouds are acidic, while the surface of Venus is an inhospitable 864 degrees Fahrenheit. However, these are just 2 planets out of potentially billions. The universe's immensity and the apparent universality of its physical laws make it seem likely that microbial life exists elsewhere. Indeed, life may have arisen elsewhere and been transported to Earth. Greek philosopher Anaxagoras first suggested this idea of panspermia in the 5th century BCE. Naturalist Charles Darwin briefly turned to this idea while working on his theory of evolution by natural selection, troubled that the accepted figure for Earth's age did not give enough time for complex organisms to evolve. Earth is now known to be vastly older than was believed in Darwin's time, so panspermia is not needed to explain the origin of life on the planet. Recent discoveries show that comets can carry many of the basic chemical components of life, but the exact mechanism by which life on Earth began remains a mystery. Solving that mystery should give a far better idea of how likely life is elsewhere. Do there exist many worlds, or is there but a single world? This is one of the most noble and exalted questions in the study of nature. Albertus Magnus, 13th century scholar. Computer simulations have shown that it is theoretically possible for simple single-cell life forms to exist inside comets or asteroids and to survive an impact like this with Earth. Where is everyone? One day, over lunch in Los Alamos in 1950, Italian scientist Enrico Fermi asked a simple question: where are they? He reasoned that, even if only a small proportion of planets play host to intelligent life, given the unimaginable numbers of stars within the galaxy, one might expect a large number of civilizations to exist on other planets. At least some of them may have chosen to send messages or tried to visit Earth themselves. Earth has been producing electromagnetic signals for 90 years or so, since the dawn of radio and television broadcasting. These modulated radio waves, expanding and extending some 90 light-years in all directions, should be a giveaway of a technologically advanced society to any potential spacefaring intelligence. In 1959, Giuseppe Cacconi and Philip Morrison suggested a bandwidth to search for alien radio messages. A year later, Frank Drake, at the National Radio Astronomy Observatory in Green Bank, West Virginia, set out to look for them. Drake founded Project Ozma, named for the Queen of Author L. Frank Baum's imaginary land of Oz, a place difficult to reach and populated by exotic beings. After a briefly exciting and noisy encounter with some top-secret military radio jamming equipment, Drake and his team were met with silence. More than 50 years later, the silence has not yet been broken. Order of the Dolphin. Drake drew together a diverse group of scientists to lay the foundations and protocols for the search for extraterrestrial intelligence. The group jokingly called itself the Order of the Dolphin, in reference to the work of neuroscientist John Lilly, who pioneered the science of speaking to dolphins. As one of the few people dealing with interspecies communication, Lilly was an important part of the group, which also included a young astronomer Carl Sagan, who was an expert on planetary atmospheres. In preparation for the Order's first meeting in 1961, Drake came up with a formula for the number of alien civilizations in the galaxy. N equals RFNFFFL. The total was reached by multiplying the factors necessary for intelligent extraterrestrials to evolve and be discovered. It depends on the rate at which stars suitable for intelligent life form, the fraction of these stars that are orbited by planets, the number of planets in any given planetary system that can support life, the fraction of these planets upon which life actually appears, the proportion of life-bearing planets that go on to produce intelligent life, the proportion of civilizations that develop technology that betrays detectable signs of their existence, and, finally, the length of time such civilizations survive. With these terms in place, bounding limits could theoretically be placed on each one. In 1961, however, not a single one was known with any confidence. Delegates at the meeting concluded that N was approximately equal to L, and a potential 1,000 to 100 million civilizations might exist in the galaxy. Although values for some of the variables in the Drake equation have been narrowed down over the intervening years, modern estimates of N still vary wildly. Some scientists argue that the figure may be 0. The Pioneer plaque contains information about the location of Earth within the Milky Way. The search for extraterrestrial life is one of those few circumstances where both a success and a failure would be a success by all standards. Carl Sagan. Message in a bottle. In 1966, Sagan co-wrote Intelligent Life in the Universe, perhaps the first comprehensive discussion of planetary science and exobiology. The book was an expanded and revised version of an earlier edition, published in 1962 by the Soviet astronomer and astrophysicist Iosif Shklovsky. Although highly speculative, the book ignited discussion among scientists. It inspired NASA's Project Cyclops report, an influential document now referred to as the SETI Bible. In 1971, Sagan approached NASA with the idea of sending a message on its Pioneer spacecraft. Sagan and Drake worked on a design that would advertise Earth's existence to alien civilizations and help them locate Earth in the cosmos. The graphics on the Pioneer plaque establish a unit of measurement using the 21 cm hydrogen emission line. Units defined by reference to Earth-based phenomena, such as meters and seconds, would be meaningless to extraterrestrial scientists. By choosing units from properties of nature, the hope was that they would be understood universally. All the images on the plaque were scaled in terms of these units. A map of bright and distinctive pulsars points the direction to Earth, and Pioneer's route is traced on a simple pictogram of the solar system. Images of a man and a woman were drawn by Sagan's artist wife, Linda Salzman Sagan. Pioneer 10 and Pioneer 11, launched in 1972 and 1973, were fitted with Sagan's plaque, etched on a 6 by 9 inches gold anodized aluminum plate. Critics warned that it would attract the unwanted attentions of power-hungry aliens. Feminist groups were unhappy that the man waved in greeting, while the woman's pose angled her body submissively toward the male figure. Salzman responded that women are smaller, on average, that having both figures waving might be interpreted as it being the natural arm position, and that she merely wished to show how the hips moved. Sagan had initially wanted